get on to working on a small body. I'm going to do this in 2 separate steps. I'm going to show how we can load the data, just show you how simple it is to get going. I'm just going to call this, just give it a very simple name. And look at the VRGS, have our across the top, which is our menu systems. We have on the left-hand side, the data collections and interpretations tree. So data is things like your meshes, interpretations, or anything that you have drawn. And then collections are just descriptions. So that might be, grain sizes, fascies, those sorts of things. Anyway, there's the main 3D window. And over here, I've got some data. And in this one, this is one of the Phobos models that I've just downloaded from one of the websites that I showed earlier on. Now, the import process is as simple as grabbing your OBJ file and doing a drag and drop into the 3D view. And it tells you down here, gives you information on the loading of the data. So it's importing the OBJ. This is actually telling us that it's importing the vertices at the moment. So to give that a little bit of time, it changes to F, importing F, that's telling it's bringing in the faces. And then we have a bit of processing to do. When you deal with these kinds of models, you have to, and particularly when you're programming with them, you have to consider the way the data is structured and how that actually influences the way you're going to be working with the data. So you see here, it's doing some processing on the data as it's coming in. The first part here is making sure that the mesh is correctly structured and that there's no redundant data in it, because you would be surprised how many data sets you load in that have got redundant data in them. And then it's doing a little bit of work on restructuring the data. This thing, building a BSP tree, is the way in which you can sort through data sets very quickly. Quite often on these models, you might have tens of thousands, if not tens of millions of vertices. So you need to be able to access them and find them and sort them and pick them very, very quickly. And that's done. So we've completed importing our model and it's appeared in our triangular meshes. So I'm just going to select that. It will do a little bit more restructuring on it, prepare it for visualization. And at this point, I can hear the fans on my machine all of a sudden start up really, because it's working quite hard, but there we are. There's our first view of Phobos. Now, when you bring any kind of data into your software, always check your data. Always make sure that it makes sense. Do not trust that that data set has come in as you expected. And the first thing that jumps out to me on this is that Phobos is obviously much bigger than 16 meters. On my scales here, it says we're going from -8 meters to +8 meters. That's obviously wrong. Now, if I just quickly do So I've just quickly Googled it, and it's telling me that Phobos is about 27 by 22 by 18 kilometers, right? So that is wrong. What's happened here is the shape file is in kilometers, VRGS works in meters. So we need to do a correction there. I'm just going to go into operations, and we're in transforms and scale. Very easy. As I'm sure you can guess, we just have to multiply everything by 1,000. Give it a moment or two. It has to rebuild the DSP tree. So this thing that we use for selecting and finding our way through the data, because now the data has changed its size. And I have to reset the view. And then there is something else I need to do here. Because it's changed its size, I have to go in and change the contour. Set 5 kilometers as well. Okay. So now we should Phobos correctly scaled to check. We'll go and put some scale bars in. So there's a scale bar. And obviously, if I zoom in to a go-to on this scale bar, there it is. That's 5 meters. It's not an appropriate size for something the size of Phobos. So let's change that. Let's make it 100 meters high. Now, even though it's 100 meters high, we still can't see it because it's just too thin. So let's make it 50 meters wide. Let's make it 1 kilometer, 1,000 meters. Let's say, because 1 kilometer should have 10 segments, we can make it even wider. We can say we want it to be a orientation of the bar. And now we have scale in there, and that's starting to give us information on everything's nicely, we know that's okay. At the moment, the color that we're using is based on the Z value. That's not that helpful. We can generate some attributes. So I'm going to very quickly let's see, what can we do here? Let's do in here. We're in development. No, I don't want to do that. I'm going to do, let's do range. Right, so what range is doing is it's creating an attribute that is distance from 0. So this creates an attribute that is the distance from the model. And to pull out a little bit information and start to just a little bit more detail. And you can see the nature of Phobos.
Dave, apologies. Can you maybe have the moving on the screen and the speaking not in sync, because the compression is working easier?
Okay, all right. Sorry, I forgot.
No worry, no worry. Thanks so much.
Yeah, and yeah, remind me again, please. I'm likely to forget because I'm get quite into working with the data. But anyway, right. So that's the start of it. Let's do, we can go a bit further with this. So we would go into attributes and tensor analysis. Now, tensor analysis is that process that I mentioned in the previous talk, where you go through every vertex and find the vertices within that particular range. So this is the sphere radius here. So for every point in this mesh, it will go through and find all the points that lie within that sphere and calculate a set of attributes. And here are the attributes that we have at the moment. And we have our basic attributes, which ones that you use on a day-to-day basis. And then we have the advanced attributes down here, which they're the sort of attributes that some of these actually very useful is the sphericity and change of curvature. These other attributes, quite often you would use those in sort of statistical analysis and machine learning kind of approaches, but they might not actually mean too much to look at them right. The color way can do it by search radius, or we can do it the number of near because this takes 10 minutes to generate the full attribute set for Phobos. So it's not really a very long time. So yeah, not really a long time. It's a one-off process. So you do it once, and then once you've saved your project, you don't have to run the attributes analysis again, and everything visualizes pretty quickly. So in that case, I'm going to come out of VRGS.
David, before you go out,
yeah,
there's a question about to show again how to correct scale the size from meters to kilometers, since the output's broken a bit.
Yeah. The scale correction is done from the triangular mesh. So you go to the mesh that you want to rescale, right click, it's in operations, transforms, scale. And then you just type the scale that you want to do it. So we did scaled by 1,000. There is actually, while we're looking at that, there is actually a slightly different way that we can do it. We can go into this option here, which makes a mesh active. And when we do that, we have a new menu appear that allows us to do various operations, translations, and scaling. Another way you can do it is you click 2 points. If you've got something you know the distance of, say if you knew the distance, you know, from there to there, or perhaps you knew the distance of one of the across one of the craters, you could just select 2 points and put that distance in. It's actually quite easy to work on outcrop data because you can model and then just do a rescale, because the photogrammetric models don't always come in at the right scale. So there's another way to do your rescaling there. Okay. So I'm going to exit, and I'm just going to load the Phobos model with the attributes already generated. And this tells us here that it's loading. You also sometimes see in VRGS, and I'm sure you're familiar with this with other bits of software, that it goes up to a certain point and then hangs around for a bit. So this, when you're loading data like this, it quite often gets to 40% and then stops there for a while. That's just sometimes it is quite difficult, depending on the process that's going on, to work out exactly how long is left to go. So anyway, you just have to, as long as it's still spinning, then you know that it's processing. And here's all of our attributes. Screen looks a bit funny, the display looks a bit funny. That's because with this, we're sitting right in the middle of one of the scale bars. So let's do our reset view. And there we are. Triaxial scale bar, 1 kilometer, slightly different place to what we had it before, but everything is correctly scaled and we're ready to go. And all the attributes have been generated. So for this example, I just generated everything. You can delete them if you needed. So I always, generally speaking, I generate everything, and then after a while, I'll start it. I don't. Some of these we have. Well, first of all, if you look at this, you can see that some string there. We can see that the craters. We can see that there's variations in here. They're quite subtle. You might find it a little bit difficult if you're trying to interpret them. This is where the attributes come in. But we'll jump straight in with dip. That's the dip of the surface. And already you're starting to see that it's pulling out quite nicely the craters and starting to pull out some of these linear features that we have. Then we have, now you have to remember back to coordinate systems that this is not this is in a Cartesian coordinate system. It's not a geographic coordinate system like we have on Earth. We're not in lat long. We're just in X, Y, Z with, so the scale bar, I'm sorry, the rows, the compass at the bottom right of the screen here is showing this as if it was a body just sitting on top of the, in front of you on top of the Earth. So we have Z going up, Y-axis going into the screen, X-axis going across the screen. Right? So that north arrow is really, really meaningless. So actually, let's go to the home screen and let's turn the north arrow off. So we're starting to pull out some features. So we've got dip. We've got the direction of dip. And then we have values like collinearity, which hasn't worked very well. But coplanarity, so coplanarity is how flat the surface is. And this is a good one for pulling out discontinuities, changes in slope. So if you have a change of slope, a break of slope, your coplanarity across that point will be low because the surface orientation is changing. So coplanarity, how flat it is. So if the surface is completely flat, I mean, it can be orientation, it can be vertical, as long as coplanarity will be high. Into our charts over here, there's a of our coplanarity attribute. From
Dave, sorry, it's breaking a bit. If you can, yeah.
Okay, I'll just, yeah, right.
In the meantime, there are a couple of questions, David.
Yeah, go on.
Asking, the opening Phobos in VRGS is not presented as we see now, and I guess the answer is because you still have to be calculated all the attributes, right?
Yes, that's right. So if you look at the details that were sent out to you, there is a link where you can download this particular model. If you want to generate your own attributes, and you've got the Phobos model loaded, it is in attributes, tensor analysis, give it a moment or two, because what it's doing here, it calculates what these values need to be, gives you a good at what these should be, and you'll just do check all. Don't mess with this. Just leave that exactly as it is, press OK, and it'll take about 10 minutes to generate, depending on your machine, obviously. When you do a process like that in VRGS, some of the processes will, if it's a big process, will just all the resources to do it. Often you find it will crash. You'll get that that means
David, sorry, we have missed all the last part of discussion because of
sorry.
Okay,
I'll is this better? Is this all right now?
Now is all right, yeah.
Okay. Yeah, it is telling me I've got an unstable internet connection. Right. Yes. So what we were saying. Yeah. So if VRGS is hang when you're doing these big processing jobs, just let it sit there. It will eventually get to the end of the processing job. Anyway, generating some of these attributes can take quite a while, particularly on big models. So it's just a bit of patience. But as I mentioned before, you just need to basically, run them once and you don't have to do it again. Anyway, here's our coplanarity attribute. From processing images, you're probably familiar with the concept of doing a contrast stretch. We can do that here. So I'm telling it to just use, these are the filters. I'm telling it just to use the color scale within just this range of values. So we've got some very flat features and some very rough features. But now we're able to see craters very, very well defined. When you come into here, you often see when we have one of these linear features that we're looking at, and you look at coplanarity, they often have more than one line. So we can see we're going from dark to bright, and possibly dark again. And we see this pattern repeating over and over again. We've got this one here, dark, bright, dark, bright, dark for a single linear feature. That's because we're going from an area of high coplanarity here, so it's flat, going round the curve of this feature, the top of it, so the coplanarity gets lower. Coplanarity gets higher at the bottom and then lower as it comes back up over the top. So that is when you've got like a ridge or a furrow or a little valley, you quite often get this doublet of features. So that's what we're seeing. It is really pulling out all of the detail structure very nicely. So we can now go in and start to interpret this data. First thing we want to do is start measuring the orientation of some of these linear features. So let's do that. I'm going to go digitize polyline here. I'm just going to track along Now, of course, when you do this for real, you'll spend a lot more time and a lot more care on your interpretation. So I'm going to quite in terms of the interpretation. I'm going to change some of the display settings to make it easier to see. We're going to use a 3 trace. I'm going to make the traces quite thick. And we're going to have a plane that's 200 meters wide, sticking out along the orientation. So there we go. First interpretation in there. And let's do another one. So can't see it there, but my interpretation is going to be that that feature goes all the way to there, continues across. Remember, this is interpretation. Match what you see on data and as possible. So there's a really good one here. Let's bring this around. Let's see if we can track this one all the way. I'm going to go digitize polyline, and we'll start here. Now, if you want to move around, this is complicated because we're going around the object here. If you hold down your shift key while interpreting, you pause your interpretation and you cannot move the model around. So I'm going to carry on. Now, is it the same feature? Maybe, maybe not, but I'm going to make my interpretation. And just for the sake of demonstration, I'm going to say I'm going to assume it's the same one that goes all the way around. And we can cut it all down. And I'm going to stop it there. Right. So there you're able to interpret all the way around. And we go to our charts. Now we're starting to see these planes, these features, linear features, are being presented on a stereo net, and we're starting to pull out the relationships between them. So there we go. Right. Now the next thing we want to do here is start to pull out some information on the craters, because we want to know the relationship between the craters and these linear features. Right, so let's just look at, we'll go to it to start with. Now, there isn't really a tool in VRGS for mapping craters. And when we started looking at this data set, thinking about the winter school a couple of months ago, I tried to work out what was the best way to do that. And the way that we've come up with is to use one of the existing tools. So I modified one of the existing tools to be able to allow us to measure the size of craters and get the orientation of them on the surface. We're using our dip azimuth tool here, and we're using it with 3 points. And now I can go to any crater, do 1, 2, 3 points, and it will give me the orientation of the crater. I need to change my display style slightly for this. And I'm going to switch on this thing, auto glyph size. So glyph is kind of the shape that you use for display things. So in for structural measurements, it's the disk with the orientation annotation on it. So I'm going to switch off. We're going to show glyphs, and I'm going to do auto glyph size on. And that is automatically scaling the size of the glyph, so the disk, to match the interpretation points. Let me just switch those on. Show vertices. I need to make those big. Big deal. There you go. Right, you can see the points that I selected on the outside of the crater, and it's created a disk that matches that size. Now, we might want to go back in there and edit it, and or maybe redo it if we're not happy. But for the moment, we're just going to add a few more in. There's a way in here we can go sticky interpretation. If you use sticky interpretation, what that means is that before, when I clicked azimuth and did 3 points, right, I'd have to go back and to do the next one. I'd have to go and click here again. Just going to make these a bit smaller. They're a bit obtrusive at that size. Now with sticky interpretation, I can just keep on adding new measurements in. Hold down the shift key to move to a new area without coming out of interpretation mode. And very quickly, you can build up quite a nice interpretation or data set on the sizes and the locations of all of these. So let's do the big one. There we go. Now, each one of these measurements, when I select it on the properties panel, it gives us the statistical information. So there's the orientation, which remember is the orientation of this in its Cartesian coordinate system. So this is, you know, as orientation like it was measuring it if it was an object in front of you on Earth. But down here, we have circle diameter. So it tells us how big these are. When we go to back to our charts, back to our study, this is where we can select this measurement. When I click on, so if I click on measurements and then give the tree focus, it highlights which measurement you've clicked on. You have to do it on the measurement of the 3D view and then click on the tree to give the tree focus, because this highlight only appears when the tree menu has this focus. Right? So I'm going to select that. That's orientation 10. Right click, set as regional. We can then go to our StereoNet and we can say, let's do correct to regional and see if there is any relationship between what we see within these planar features to the orientation of this big crater. So you can start to look at evidence to see whether there's a pattern, the patterns that you would expect to see from the fractures from a meteorite impact on something like this. And Matteo showed that animation in his talk where some modeling had been done. So you have some ideas of what kind of impacts would be. You know, maybe that's on another comet, but principles are the same. You've got sort of ideas of how the stresses would cause fracturing, and then you can compare what you see in that scenario to what you have on your actual results. Okay, so that is how we can get quite a lot of data and measurements from something like Phobos, going from importing the data to actually doing some interpretation and getting some results out. And hopefully you can see that you can go quite a long way very quickly from in the shape model. The attribute analysis the 10 minutes on top of what we did, but we can get in there and make some orientation measurements quite easily. Okay. So I think with that, it's time to, unless anybody's got any questions, we can switch to looking at 67p.
David, there is a question. Maybe it's not strictly related to what you showed now.
Yeah.
But it's something related to the license. So as some people are not able to get the license working. It says license spring exception encountered. So I don't know if you know.
Okay. That usually happens if VRGS can't access the license spring server. So that might be a firewall problem. The other thing to do is sometimes just trying it again a bit later on. Usually if it's a firewall problem, VRGS would tell you that it can't connect to the license spring server, and it will tell you to use the offline licensing approach. But if it's not asking you for offline licensing, it's nearly always network connectivity issue. It could be the License Spring service. So License Spring is a company that does that handles the licensing side of things. If their server is offline, which but not very often. Internet connectivity issues, like Zoom is telling me I have at the moment, then that can be a problem. So just try again. If you continue to have problems, just send me an email, and you can do that. And you know, I guess through the Winter School, but otherwise, just go to the VRGS Science site, and there's a support form you can fill in. Just say I'm having trouble, and I can check the license server. But I can see that a lot of people have activated the license that was sent out. So I would say it's probably network issue.
We have another couple of questions. First one is about when you load the project, you get the blank screen instead of Phobos data. I guess that they have to activate the mesh, right?
Yes, yeah. So when you go into, you have to switch your model on, because otherwise you get a blank screen. So yeah, make sure that
there, but it has to be visualized. So
yeah.
Activated.
You can, on some occasions, I know there is on rare occasions that sometimes it can appear checked and not displaying. If that does, click off back on again.
And maybe there's a question for more for Matteo, but I think it's linked to one of the publications that you showed about the origin of the lineations. And yes. Another one, you can answer on that, and then I will address the new one to David before moving to the comment.
Actually, both of them could be answered by me because they are related. So okay. The first question is why we have these lineations. Actually, it was in particular in 2014-15. And even here now, it's a lot debated on which is the reason why we have this kind of lineation, which could be their interpretations. So there are several hypotheses. The first one is that they could be fractures, okay? And this one is one interpretation. Another interpretation is that they could be a ray ejecta from the craters that you see on the surface. So some secondary, if you want, impacts from generated by the impact of the craters that you see on the body. The third one, it's very particular. So you have to imagine that you may have impacts on Mars, okay? The ejecta on Mars can reach Phobos and create these grooves all around Phobos. So these are the three main, I would say, hypotheses that has been put forward for understanding and explaining these lineaments, these grooves. For one of them, it would be very easy to see if this hypothesis is, I would say, has some possibility to be. For example, the hypothesis, in particular, the hypothesis of these grooves being generated by an impact, okay, as a secondaries, you would expect some rayed secondaries, so some orientation of these grooves that should be radial to the impact itself. This make me to go to the second questions. The questions why we change the reference system, and we can use a reference system in relation to a given feature on the surface. And this is the reason. If I want to check quantitatively if these lineations are related to a crater, for example, I can put the reference in relation to the crater itself, so that, for example, if I would expect that all my grooves would be radial, as one of the hypotheses may envisage, I should take the regional plot, take into consideration a given crater, for example, the big one there that is called Stickney. So if I want to see if all the grooves are radial, or I want to visualize that in the stereoplot and measure them, I can plot as regional, take into account the Stickney crater. In this way, I would expect, for example, a radial distribution even on the stereoplot, and I can understand how much misfit, which is the deviation of the lineaments with respect to the crater. And it's obvious also looking at them that there is no real relationship of fractures with the crater that we see there. The other two hypotheses, there is the hypothesis of fractures. It is something that is still can be still interpreted in this way, looking if they are both radial or concentric to a crater. And again, the regional representation could be good. And on the basis of what we have already done, we have seen that there is no clear relation. So some of them can be related to some of these fractures, but many are not related to the impact itself. So the Stickney crater was not able to create such a persistent and long grooves on the body itself. So if we consider this groove as created by fractures, they should be inherited grooves, and this can have some other implications. And the other implications is that we don't know Phobos from where it comes from. So it can be a captured body, or it can be aggregated together with Mars as after, I would say, a primordial impact, like I would say something like the moon, if you want. Could be a later aggregation of material that has been ejected from Mars, for example. And if we see the fractures and we see that they are not related with this impact, we should interpret this body as a body that has derived from a parental body, a bigger body that was impacted, and this big body could have had before fractures. And so what we see could be fractures of the parental body that has been inherited, and this will bring some points towards the capture hypothesis of the origin of the body. And let's now go to the last point, which is this could be grooves that has been generated by material that is impacted Phobos and coming from Mars, okay? And this is good because sometimes we see that these grooves are cross-cutting some impacts. And if they are cutting some impacts, they should be later, okay? And so even this hypothesis that was put forward in 2014, I think by Murray or something like that, could be good because we see these intersection patterns in which in some cases the fracture are cross-cutting some craters. So, and also they have found some hydrated mineral on Phobos that may, I would say, favor the hypothesis that some material from Mars arrived to Phobos, not exactly eventually forming the grooves, but potentially. So these are, for example, other planetary scientists doesn't think there is a unique explanation for this fracture. They could be good, at least the interpretation of the grooves from ejecta from Mars could be good as well as fractures. There are some of them that could be even due to the impact there. So some planetary geologists like Ed, for example, thinks that these grooves have a different origin. And to disentangle that different origin, probably we would have needed some tools like this one, as were GS, in which we can actually draw one by one. It has not been done yet, and see the intersection pattern between them and try in that way to interpret. And there should be even some dynamical model that can explain a little bit better the interaction between the ejecta from Mars and Phobos. Sorry to have been long, but these two questions were actually long to answer because they have many implications.